Okay, so today we will discuss the particle accelerator. We will start the discussion and then we may continue it to the next lecture. All right, so first let us see why do we need particle accelerators. If you remember the Rutherford scattering, basically we had alpha particles bombarded on targets like gold and silver or gold, aluminum, etc. Okay. So, these alpha particles were obtained naturally from radioactive sources. So, the limitation, the energy available for these alpha particles are limited depending on what the source or the parent that are decaying into what daughter, the alpha particle energy is fixed, and then we can actually expect some kind of order of an MeV energies for this kind of natural radioactive alpha particles. So, energy of these alpha particles are typically a few MeV, mega electron volts. Now, as we saw in the case of Rutherford scattering experiment, such alpha particles will not really penetrate the nucleus, but will actually scatter off the nucleus. It gives good information about the atomic structure, but it will not be able to probe the nucleus, the interior of the nucleus, because the energy of the alpha particle is not enough to penetrate the nucleus and then go inside and then understand the dynamics there inside the nucleus. So, to get higher energy particles, let us say not only alpha particle, but any other projectiles, we need to artificially or we have to accelerate them by using some mechanism. Okay? We need something like accelerators. So, these accelerators some particular mechanism using which we can accelerate these particles. So, most of the time our projectiles are charged particles. So, let us focus first on charged particles. Okay. We could also do nuclear experiments with the neutrons, which are electrically neutral particles, but we will not talk about accelerators of neutron, etc. But we will be able to actually talk about accelerators of charged particles. So, charged particle experience Coulomb force in an electric field. And the electric field, if electric field is E, the force is Q times the charge of the particle times the electric field. So, Q here is the charge of the particle, E is the electric field, and if you place a charged particle in an electric field, it will experience a force magnetic, the amount of the force will be Q times E, and this force will accelerate this particle, and the direction of acceleration is also fixed to be in the direction of the electric field if it is positively charged, and if it is negatively charged, it will be in the negative direction. Only question is how much of the electric field can be actually attained in practice, and how do we, and correspondingly how much of charge energy can be given to this accelerated particles, or to what energies can we actually accelerate these particles, whether we can take the energy of these projectiles to ions, charged particles to hundreds of MeVs or beyond that, and what kind of an electric field is needed for that, and whether we can achieve this, or what kind of an arrangement can actually lead to such high voltages or high electric fields, is the kind of questions that one has to ask. So, this kind of accelerators are based on Coulomb force or electrostatic force. So, we call them electrostatic accelerators. Okay. So, electrostatic accelerators are based on the Coulombic force experienced by charged particle. So, one such as I said, how to attain large E or consequently or high voltage difference between two terminals, I mean. So, this is the question that one has to ask. So, one such arrangement is due to Cockcroft and Walton. What did they do? They used low voltage source of alternating current or low alternating voltage, okay. Say some low voltage V 0, which is the peak voltage, say, and made some arrangement. If you look at an arrangement like arrangement of rectifiers and capacitors like this, say a capacitor here and then connected through a rectifier like this, and this one in turn is connected to another capacitor through another rectifier, and again you can have another capacitor and a rectifier, and you can continue this like this. Okay. So, this type of an arrangement will lead to voltage multiplication. So, what happens is, let us say this point I call A, B, C, D. So, if you look at this arrangement and then if you know your electronics and how the current flows through a circuit like this, alternating with an alternating voltage source or current source, then you will see that if V 0 is the peak voltage there, when the capacitor C 1 is fully charged, point A will have a peak voltage of 2 V 0, because the other rectifier R 1 will actually give a voltage V 0 there, and because of the capacitor there will be a voltage, alternating voltage V 0 there. So, it will be A will have a peak voltage of 2 V 0, and this will be directed to B as a DC voltage, and B will experience a DC voltage of 2 V 0. So, V B is equal to 2 V 0, and this continues. Okay. This is directly transferred to C, okay, 2 V 0, and the other capacitor C 1 and C 2 will actually give an oscillating potential voltage of 2 V 0 there. So, peak will there be 4 V 0 and this is directed to point D through the rectifier connecting C and D, and V D will have a DC voltage of 4 V 0, and then if you continue this arrangement you can get multiples of this V 0, higher multiples of this V 0 at other points. So, this way one can think about getting a large voltage from a small voltage. Okay. So, this is the arrangement that was used by Cockcroft and Walton in their experiments, and then there are a lot of modifications to this. This is one such arrangement. Then you can have slight modified versions of this, improved versions of this, and usually the voltage that you will achieve is something like 1000 kilovolt, etc., with this kind of arrangement or of that order. Okay. And the simplicity of this is the issue here. I mean, it is very simple. So, even now you can think of using it for small voltage, I mean small accelerators, where you need not so high acceleration, but at the primary level of different accelerators also this can be thought of as using. Okay. Then another kind of accelerator is called Van de Graaff accelerator or generator. So, Van de Graaff generator which generates high voltage. So, the principle here is simple. If you have a conductor C 1 and another hollow sphere, conducting hollow sphere C 2. So, there is an inner conductor conducting sphere C 1 and an outer conducting shell C 2. Okay. So, now if you have some charge on C 1, say some positive charges here. If you connect these two electrically, then the properties of electrostatics that we know tells us that all the charge on a conductor now will reside on the outer surface of this conductor. Okay. This is because there cannot be any electric field inside the conductor. So, if there is electric field inside the conductor, because the conductor has free electrons in it, okay, or free charge in it, it will actually make it flow from one point to the other and attain some kind of an equilibrium where the surface of the the conductor is an equipotential, and it should be, if you look at it properly, you will see that the inner surface of a hollow conductor will not have any charge, or in this arrangement when they are connected, C 1 and C 2 are connected, they are become part of a single unit, and C 1 can be thought of as an inner part of the whole arrangement, and therefore, there will not be any charge on it, and all this charge will actually flow to the outer surface of this arrangement, which is the C 2. So, the charge will flow, and it does not matter if there is already some charge on that, and then what is already some charges residing on C 2. Okay, it does not matter, all the charge from C 1 will flow to C 2. Okay. This is a property of conductor. Now, you think of an arrangement by which you will actually have kind of a big conducting dome. Okay. We will not close it fully, but kind of a almost full spherical shell, but with an opening and an inner sphere, conducting sphere. Okay. Same arrangement C1 and C2 say that is we have. So, suppose I mean if we connect these two, right, if we connect C1 and C2 electrically, then if C1 is somehow charged, suppose we can charge the C1, all those charge will go to C2. So, okay. The only question is to charge this C1. For that, people thought about some arrangement like this. They connected C1 with the some insulating belt, and this insulating belt is connected to some other drum, and it can be now continuously rotated, say, right. The belt can move continuously by rotating this using a motor, and if we can pump in charge here, and if we can actually charge this belt, the belt is made of insulating material, the charge will be fixed on that. It will continue carry this charge to C1, and when it reaches C1, since C1 is a conductor, it will take that charge, it will then transfer this charge to C2 through the connector. Only question is to charge this one, and then there can be some kind of a arrangement to charge this belt by applying some voltage difference between these two, and then ionizing the air or gas at that point near the belt, and the charge, the positive charge is repelled from this thing because of the battery there, and the voltage is so that it will repel this positive charge. It is one particular way of thinking about it, and then that positive charge can be deposited onto the belt. And since the belt is continuously moving, it will carry this charge to C1, and C1 is connected to C2, and then C2 will get this charge. So, C2 will be continuously charged like that, and then there will be lot of charges here, and with respect to ground, therefore, this will have a very high voltage. Okay. So, now one of the problems that you can think about is the breakdown. If you keep this arrangement in air, high voltage breakdown or sparks will be there. So, you can ask the question, what is the voltage that I can achieve if I keep this in air, and you can take this voltage even to higher energy, higher voltages by actually keeping the whole C2 arrangement in a C1 and C2 arrangement in a container which has insulating gas, not air. Air also breaks down at some high voltage, and if you have some other gas, insulating gas, which will not break down at higher voltages compared to that of air, and then you can fill this container with such insulating gas and put this C1 and C2 arrangement, this terminal, let us say this is called this high voltage terminal. So, high voltage terminal inside such pressurized insulating gas, then we may be able to achieve even higher pressure. So, that is what is practically done. And how do you use this to accelerate particles? What you have to do is to take this arrangement. So, now let me draw the schematics of this high voltage terminal here, And if I have source, ion source, say let us say I want to accelerate some particular ion. Okay. So, I keep this ion source inside this high voltage terminal and generate this, let us say it is a positive ion. So, if it is positive ion, it will be repelled by this high voltage and it will push it down through the tube, accelerating tube, and you can keep your target at T. So, target at the other end of the accelerating tube, and these ions will hit the target with high energy. This is one way of thinking about it. The one drawback of this arrangement is that you are keeping the ion source inside the high voltage terminal, then only it will push this voltage, this ion down to the target. Now, supposing you want to change the source, change your experiment, and then you want to actually use a different source, or supposing something happens to the source and then you want to take that out. So, the access to the source is very much restricted in this kind of an arrangement, because if you want to take it down, you have to discharge the high voltage terminal, which must have taken some time to charge it to high voltage firstly. So, now you have to discharge it completely, then only, and then again we said that usually we keep this in a high pressured insulating gas. So, you have to actually pump the gas out and then open that tank, and then only you will be able to access the ion source. Then if you want to actually replace this by a different source or the same source, then you will have to again do the process, redo that. So, this is actually not very a convenient arrangement. So, people thought about a different way of doing it. Okay. So, that takes us to tandem accelerator. So, tandem accelerator principle is the same as the Van de Graaff generator accelerator. Only difference is that now you have the accelerating tube. Suppose you are interested in some kind of a particular positive ion. What you do is to actually generate the corresponding negative ion source ion. Okay. Basically, I mean you can actually deposit electrons by some mechanism. We will not discuss how it is done, and to the atoms of interest, and you can have the ions there in that, okay, negative ions. So, now if the tube is so that you have the high terminal, high voltage terminal somewhere in the middle of this tube, okay. The tube passes through this high voltage terminal. So, then this high voltage terminal now will attract these negatively charged ions. So, it will accelerate this, right, okay, accelerate this, and then you keep some electron stripper. So, this is the stripper. So, what does the stripper do? Stripper, let us say by some way strips the ion of the electrons. So, it will take away the electrons. Let us say not only the excess electrons which makes the negative ion, but also some additional electrons. So, that it is now a positive ion. So, the stripper strips off some of the electrons and makes it a positive ion, and then these positive ions are now in the high voltage terminal, it will actually repel it. So, it will actually be repelled, and then let us say it has already a speed with which it is coming in, and it will continue moving in that, but because of the high voltage terminal it will actually be pushed out. So, it will be pushed out with high again high, some force, and therefore, it will change, it will increase its energy, okay, increases, and then target can be kept at the other end of the tube, and then it can actually the high energy ions can now hit the target here, and then we can perform our experiment. So, this arrangement is called the tandem accelerator. So, here the ion source is outside the arrangement of high voltage terminal, etc. So, it is easily accessible, and then we can actually have a easy replacement, etc. So, one can achieve something of the order of 100, 10 to 100 MeV energies can be achieved with this kind of arrangement. Okay. This is another electrostatic accelerator. Now, moving away from electrostatic accelerators, we can think about cyclotrons. What are cyclotrons? So, these cyclotrons accelerators use not only the electrostatic force, but also make use of the Lorentz force experienced by moving charged particle inside a magnetic field. So, we know the Lorentz force on a moving charged particle moving with velocity v in a magnetic field B is q v cross B. If V and B are perpendicular to each other, then we can say the magnitude is simply V B times Q. This will be acting perpendicular to both V and B. So, let us look at the magnitude of this one. Since F is perpendicular to V, it will not actually accelerate it. Okay. So, it will not increase V, it will actually make it bend, okay, and move in a circle. So, the particle will be moving in a circle. All right. Motion of particle in a circle, and the centripetal acceleration is v square over r here, and that should be equal to the force. So, that will give us q v b, which is the force here, external force acting on that charged particle. This should be equal to mass times the acceleration. So, it does not really increase the speeds, but it actually does something else. It does not change the energy as such, it but changes the direction of the motion. So, it will actually move in a circular path. So, q v b is equal to m v square by r. So, r, the circular radius of the circular path, is equal to m v over q b. Okay. It is a circular motion, and what is the period of this circular motion? It is 2 pi r is the distance that it will cover once it moves around in a complete circle. That divided by v will give you the time taken for that, or v times whatever is t, capital T, the period, is equal to the distance 2 pi r. that is what we call period. So, this if I put the expression for R in terms of m v and q b is equal to 2 pi m divided by q b. V and V cancels and then T is equal to 2 pi m over. Let us keep this in mind. How do we use this to accelerate particles? All right. So, for this we will think about the following arrangement. We will take two circular discs. We will take some kind of a hollow discs, okay, and call it D1 and D2. So, let me draw that. So, this is actually a disc. So, one is D1, the other is D2. So, two identical two discs of identical dimensions, say they are hollow discs of identical dimensions placed with some little separation between them. Okay. Well, discs meaning these are semicircular discs, and now let us say that it is in a plane, keep it on a horizontal plane for example, then apply magnetic field perpendicular to the plane of the disc. So, keep this D1 and D2 in a region with magnetic field B, so that the plane of the disc is perpendicular to the direction of B, or the direction of B is perpendicular to the plane of the disc. Now, if you have an electric connection between this D1 and D2, suppose you connect this D1 and D2 through some voltage, alternating AC voltage, and then you will see that there will be electric field generated between in the gap between D1 and D2. This electric field will be oscillating. The oscillation frequency will depend on the is equal to the oscillation frequency of the source, voltage source. And now, let us say we place a charged particle in the region or in the gap, in the region between the discs. What will happen? The electric field will apply a force on this, and the charged particle, let us say we take a charged particle with positive charge, and when it is placed there in the gap, the electric field direction is from D1 to D2, then it will move in that direction. When it moves in that direction, it will enter D2 with some speed. Of course, the magnetic field will also be acting on that, but in the gap when the electric field is acting on it, the magnetic field, the force due to magnetic field is negligible. You can check that out. But once inside D2, there is no electric field, because the entire D2 is the electrode, and all of that say is. So, this is basically we will assume that it is a conducting, it is an electrode, it is a conducting disc. So, there is no field inside that, electric field inside that, but there is a magnetic field perpendicular to the speed, the velocity v. So, we will have the motion like moving the charged particle will move towards this. Inside that it will actually, because of the force due to the magnetic field, it will move in a circle, and once it comes out of this, after traversing a semicircular thing, it will come out of D2 into the gap, and let us say, so when it comes out, it will experience force due to the electric field in the gap. But now, this electric field, the force due to this electric field depends on the direction and magnitude of the electric field. So, if we arrange the oscillation of the electric field inside this gap, so that the electric field switches the direction as the particle comes out from D2 into the gap, okay, then it will continue moving, it will be accelerated further and enter D1 with larger velocity. So, the velocity with which it, the speed with which the particle enters D2 is the same as the speed with which it come out of D2, but once it comes out of D2, there is electric field now, so that it will accelerate it further, and it will go in a larger, move in a larger circle, and as it comes out of D2 with the same speed, it will again experience the electric field, and we will actually switch the electric field at that time, and then again it will switch the direction of the electric field, and then it will again accelerate towards D2, and as it enters D2, it will have a higher speed and higher energy. So, it goes on like that. Okay. So, in this way we can get higher and higher speeds and over larger and larger energies. So, let us see what was the expression for our time period of this. Okay. Time taken for charged particles to come out of one disk after entering this. So, the time between entering the disk and coming out of the disk is the time period, or is half the time period of this one. So, the T by 2 is pi m over q b. So, T by 2 is the time taken by the particle to enter this and come out of this. You see that this does not depend on the speed, it is a constant, it is the same speed, same for any whatever the speed with which it enters. It only depends on the charge of the particle, which we are not changing, the mass of the particle, which again we are not changing, it is the same particle, and the applied magnetic field, which we can keep constant. So, the time period or half time period, which is needed for the particle to enter a disk and come out of the disk, is the same, and this is the time in which the electric field should be switched, right. So, the frequency of the oscillating field, which is the same as the frequency of the AC supplied, AC voltage which is supplied, should be. So, the frequency of AC source should be equal to 1 over T for this electric field to be switched as it comes out of one disk, and then again switched when it comes out of that disk. Then only this acceleration will work, otherwise it will decelerate it or send it back to this one if the electric field is not synchronized like this. So, this should be equal to 2 q b over 2 pi m. So, we can certainly adjust our AC voltage frequency, so that it is equal to q b over 2 pi m, or for whatever particle that we are considering and whatever charge of the particle that we are considering and whatever B we are considering. And this way we will be able to accelerate this. And what did we achieve compared to the earlier accelerators? One thing that we have done is we have not, I mean, in the earlier case, electrostatic case, if we want to have higher and higher energy, what we have to do is to have larger and larger potential difference. So, the main problem there is the high voltage terminal. To achieve that high voltage terminal and keep it stable without breaking down. Even if you use insulating gas, still there is a limit to which you can go by that. And then again achieving that itself is not a simple job to very high voltage difference. On the other hand, this arrangement that we just now discussed, which is called the cyclotron accelerator. The principle here is very simple. We make use of the magnetic field to make the particle pass through the same electric field, same region of where the electric field is and small or constant electric field again and again and again and again. So as to achieve larger and larger acceleration, larger and larger speed. The acceleration remains the same, q f is the same, f is q times e, but since the initial the speed is changing. So, we have larger and larger speed and the particle will come out with very high speed with even with small applied electric field. The limitation of this kind of a cyclotron is the following. You need to what is the maximum V that we can think about? So, V, the speed we said, okay, is equal to q b r over m. So, if capital R is the radius of the disc, that is the maximum speed that we can have, which is q b r over m, and the corresponding kinetic energy T max is half m v max square, which is q square b square r square over 2 m. This is the magnetic large. So, either you apply very large magnetic field, which again is costly, and or you have a very huge large disc. Again there is a limitation that we can think about to achieve this thing. So, the entire region has to be magnetized, that is again very costly. So, these are the limitations of this, okay? And now we have to think about ways to improve that. But this cyclotron idea is certainly a betterment or improvement of the simple electrostatic accelerators. So, we will discuss some other improvements and ways to actually take it to higher energies with some different arrangements, and discuss those in the next lecture.